Welcome to RoRe Academy YouTube Channel 2.0. Our new and improved channel is dedicated to showing you how things are put together, from concept to prototype. Here, we break down the art of designing, assembling, and testing real engineering systems, helping you understand the science and creativity behind innovation in power electronic-centric systems and devices in our 5-minute video clips. Before we go into today's lesson, let's take a quick look at an incredible diagnostic tool that every EV engineer or enthusiast should know about, the enthusiast Ultra EV. This is a next-generation full-system diagnostic scanner designed for electric, hybrid, gas, and diesel vehicles. What makes the Ultra EV stand out is its ability to perform a comprehensive analysis of electric and hybrid vehicles, including advanced topology mapping and battery pack analysis. You can perform diagnostics via an OBD connection or directly through the included specialty cables and jumpers, perfect for in-depth testing of high-voltage battery systems. The 12.9-inch touchscreen tablet provides a clear, detailed view of your diagnostic results. Now, let's see how this powerful diagnostic tool is set up and operated in real time.
Our EV-related diagnostic software on our Ultra series of tablets. New Energy, green button. And this is going to be the button that you'd want to see. Quite a robust selection of vehicles that are EV software pack test. And you'll notice that once we connect to the car, it's going to give us a little bit of disclaimers, some high voltage safety related information. I'm going to go ahead and communicate with the vehicle. I'm going to select the blue button here that says battery pack information, and it's going to pull up a whole host of diagnostic information to help you repair that vehicle. So the first screen that comes up is our module status. You can see some overall general information at the top of the screen of different information about the battery pack, the state of charge, the state of health, the total voltage. But then at the bottom, we're going to see the infrastructure of how many modules this particular battery pack has. In every module, there are several cells. So if I have the button at the top of the screen that's called cell status. Cell status allows me to look at the individual cells of all the modules all at once. So I have a couple ways I can view it. If I hit the 4 little squares, it allows me to see all the actual voltages. The ones in red and blue represent the highest cell voltage and the lowest cell voltage from the battery pack, and it tries to balance them to be equal. At the top of the screen also, we have the battery pack info button. This gives me all the information that I need about this battery pack. Very helpful for, at the top of the screen, is the other live data button. So here is all the other data that the BMS, the battery management system, is allowing us to see all at once. And just like every other part of your diagnostic.
Hey guys, if you're into EVs or work with electric cars, you need to check this out. The enthusiast Ultra EV diagnostic scanner is seriously one of the best tools out there for deep dive battery diagnostics and full system testing on electric and hybrid vehicles. It's fast, accurate, and super easy to use. Honestly, a total game changer if you're serious about understanding your EV inside and out. So if you want to grab yours, just click the link in the video description below and check it out. Now, let's get on with today's video, titled Tesla Model S Battery Module. Have you ever wondered how an electric car, sleek, silent, and lightning fast, gets its power? It all starts deep inside the battery pack, where thousands of tiny cells work together like a perfectly tuned orchestra. Each one stores just a few volts, but when connected in carefully designed series and parallel networks, they create enough energy to move an entire vehicle. Today, we'll dive beneath the surface of the battery electric vehicle, or BEV, to explore how these small cells are arranged, cooled, and managed inside the battery module, the true heart of every electric car. From cell chemistry and wiring to cooling systems and safety design, we'll break down how all these pieces fit together to deliver the incredible performance we see on the road. So sit back, hit that like button, and let's explore what really powers the future of electric mobility. the BEV battery module. Today, we'll be taking a closer look at how battery modules are arranged within the battery pack of a battery electric vehicle, BEV, one of the most critical aspects of EV design. In this video, we'll explore the Tesla Model S battery pack, known for its sophisticated layout and engineering precision. You'll see how individual battery cells are grouped into modules, how these modules are connected electrically and thermally managed, and how their arrangement impacts performance, safety, and energy density. By the end of this video, you'll have a clearer understanding of why the battery pack is often called the heart of an electric vehicle, and how careful design choices influence everything from driving range to charging efficiency. The Tesla Model S, a true benchmark in electric vehicle engineering. Produced by the American automaker Tesla since 2012, the Model S is a fully electric, four-door luxury sedan that combines stunning performance with cutting-edge technology. Depending on the variant, it offers an impressive range between 628 and 840 kilometers, powered by a 100 kilowatt-hour lithium-ion battery pack. Under the hood, the Model S delivers between 493 and 809 kilowatts of power, translating to breathtaking acceleration, from 0 to 62 miles per hour in just 2.1 to 3.2 seconds. This remarkable blend of speed, efficiency, and innovation makes the Tesla Model S not just a car, but a showcase of what's possible when advanced power electronics and battery engineering come together. The Tesla Model S, sleek, powerful, and one of the most advanced electric cars ever built. But what exactly makes this machine tick? Let's break down the three main components that define its performance and technology: the car body, the drive unit, and the battery pack. First, the car body. Made primarily from lightweight aluminum, it's designed for both strength and aerodynamics. Every curve and contour reduces drag, improving efficiency and range. Inside, Tesla combines minimalism with cutting-edge technology, from the massive touchscreen to its advanced autopilot sensors. The body isn't just about looks. It's a key part of the car's energy efficiency and safety. Next, the drive unit, the heart of Tesla's performance. This unit combines the electric motor, inverter, and gearbox into a single compact system. The result? Instant torque, lightning-fast acceleration, and near-silent operation. Depending on the model, the Tesla S can go from 0 to 60 miles per hour in as little as 2.1 seconds, faster than many supercars. And finally, the battery pack, the real powerhouse. It sits low beneath the floor, giving the car a low center of gravity for better handling. Inside are thousands of lithium-ion cells working together to deliver a range of up to 840 kilometers on a single charge. Tesla's thermal management system keeps the battery at the perfect temperature, ensuring both safety and longevity. The Tesla Model S battery pack is made up of an incredible 7,104 individual 1865 lithium-ion cells. These cells are not all connected in one massive assembly. Instead, the pack consists of 16 identical battery modules, making it easier to manage, cool, and maintain. Each module contains 444 cells, arranged in a 74 parallel and 6 series, 74P6S configuration. This clever design allows Tesla to achieve the desired voltage, capacity, and thermal balance needed for high performance and long driving range. Through this modular approach, Tesla ensures that the battery pack delivers both power and reliability, while also simplifying manufacturing, testing, and serviceability. A true example of engineering excellence in electric vehicle design. Tesla uses 18,650 Li-ion cells manufactured by Panasonic for their Model S and Model X variants of cars. The battery cells used in the Tesla Model S are called 18650 cells, and here's what that name actually means. These cells are cylindrical in shape, and each one measures about 18 millimeters in diameter and 65 millimeters in height. So the name 18650 isn't random. It's a simple code that tells you exactly those dimensions. If we split the numbers into three parts, the first two digits, 18, represent the diameter in millimeters. The next two digits, 65, represent the height in millimeters. And the final digit, 0, tells us that the cell is cylindrical in shape. So whenever you hear 18650, You're hearing the cell's size and shape built right into its name. 18 millimeters wide, 65 millimeters tall, and cylindrical. It's a simple naming system, but it's what helps engineers around the world quickly identify and design with these cells, the tiny powerhouses that drive the Tesla Model S. Each 18650 cell inside the Tesla Model S might look small, but it's packed with a remarkable amount of energy. Let's break down what one of these tiny cylinders can actually do. It has a nominal voltage of about 3.66 volts, a capacity of 3.4 ampere-hours, and that gives it an energy content of roughly 12.4 watt-hours. That's about the same amount of energy it takes to power a 12-watt LED bulb for 1 hour. But what really makes this cell impressive are its energy densities. It has a volumetric energy density of around 755 watt-hours per liter, meaning it stores a lot of energy in a very small space. And its gravimetric energy density is about 254 watt-hours per kilogram, so for its weight, it delivers a powerful punch. Each cell weighs just 49 grams, yet when you multiply that by the thousands of cells inside a Tesla battery pack, you get the incredible range and performance that make the Model S one of the most advanced electric cars ever built. Tiny, light, and unbelievably efficient, each 18650 cell is a small piece of engineering brilliance that, when combined with thousands of others, powers the future of electric mobility. Now, each 18650 cell in the Tesla Model S has a nominal voltage of about 3.66 volts. That's great for a single cell, but not nearly enough to power a car. So, how do engineers increase the voltage? By connecting cells in series, end to end, just like stacking batteries in a flashlight. When you connect two cells in series, their voltages add up. So, instead of 3.66 volts, you now have 7.32 volts. And if you connect a third cell, the voltage rises again. 3.66 volts times 3 equals 10.98 volts. This is the basic principle behind every battery pack. By connecting multiple cells in series, Tesla can build up the high voltage levels needed to power the motors efficiently, while still using tiny, standardized cells. So, by simply linking more cells together, we can go from a few volts to hundreds of volts, turning small battery cells into the powerful energy source that drives the Tesla Model S. Inside each 18650 cell, there's a lot more happening than meets the eye. What looks like a simple metal cylinder is actually a highly engineered electrochemical system, carefully designed to store and release energy safely and efficiently. At the heart of the cell, we have two main components, the anode and the cathode. These are the positive and negative electrodes, and they're separated by a thin microporous separator, which prevents them from touching while still allowing ions to pass through during charging and discharging. At the top, we have the positive terminal and the positive tab, which connect the cell to the rest of the battery module. The entire assembly is enclosed within a metal case, usually made of steel or aluminum, providing both mechanical strength and protection. And at the base, there's a bottom insulator, which keeps the internal components electrically isolated from the outer casing, ensuring the cell operates safely under all conditions. All of these layers, the anode, separator, and cathode, are wound tightly together in what's called a jelly roll structure, maximizing the surface area and energy storage within that small cylindrical shell. So, even though the 18650 cell looks simple from the outside, its internal structure is a masterpiece of precision engineering, carefully designed to deliver high energy, high safety, and long-lasting performance in every Tesla battery pack. Each Tesla Model S battery module is made up of 444 individual lithium-ion cells, carefully connected to deliver both high energy and high power. These cells are arranged in what's called a 74P6S configuration. Let's break that down. The 74P means that 74 cells are connected in parallel, side by side, to form one group. When cells are connected in parallel, their voltages remain the same, but their capacities add up, allowing the battery to store more energy. So in total, you have 6 series groups, each containing 74 parallel connected cells, making up 444 cells per module. This smart combination of parallel and series connections allows Tesla to build battery modules that are not just powerful, but also efficient, safe, and perfectly balanced for the performance demands of the Model S. In a parallel connection, the voltage of the configuration remains the same as that of a single cell, but the capacity increases because the cells share the current load. Since each 18650 cell in the Tesla Model S has a nominal voltage of 3.66 volts, a 74P grouping, that is, 74 cells connected in parallel, also yields a total of 3.66 volts. Now, when we move to a series connection, things work a bit differently. Here, the positive terminal of one cell connects to the negative terminal of the next cell, and the voltages add up. So, when 6 of these 3.66 volt parallel groups are connected in series, the total voltage becomes 22 volts. In the Tesla Model S, the entire battery pack is a masterpiece of engineering, combining power, safety, and precision. Inside the battery pack, there are 16 individual modules, each built using the 74P6S configuration we discussed earlier. These 16 modules are carefully assembled together inside a strong aluminum battery tray, forming the heart of the vehicle's energy system. Each module is connected in parallel to a central bus bar through M8 bolt terminals located on the module ends. This bus bar acts like the main power highway, collecting electric current from all 16 modules and channeling it efficiently through the system. The collected current then flows to a high-voltage contactor, which controls the power delivery to the electric drive unit, the component responsible for turning that electrical energy into motion. Altogether, the Tesla Model S battery pack generates a total of about 22 volts per module, combining to produce an overall system energy of around 84 kilowatt-hours, enough to power the car for hundreds of miles on a single charge. So, while it looks like one solid block of energy, the Tesla battery pack is actually a sophisticated network of precisely connected modules, all working together to deliver the incredible performance, range, and efficiency that Tesla is known for. Here, you can see the top view of the module, along with a schematic illustration that highlights how all these components fit together inside the aluminum housing. In addition to the thousands of battery cells assembled inside, each Tesla battery module also contains a range of critical supporting components, all working together to ensure safety, performance, and reliability. These include the cooling system. Now, one of the most fascinating parts of Tesla's battery design lies in its cooling system. The pipes carrying the water glycol coolant solution inside the module feature a patented wavy design, a clever engineering solution developed by Tesla. This wavy structure isn't just for looks. It serves two critical purposes. First, it increases the surface area of the pipe, allowing for better heat transfer between the coolant and the battery cells. Second, it improves packaging efficiency, enabling Tesla to fit more cells within the same space while keeping them evenly cooled. The result is a highly efficient thermal management system that maintains the ideal temperature for every cell, maximizing battery life, safety, and performance. The image you see here is taken directly from Tesla's patent document, showcasing the ingenious wavy coolant pipe design that keeps the battery pack running cool and consistent, even under extreme driving conditions. The cooling pipe itself is wrapped in a thermally conductive yet electrically insulative material. This clever combination allows heat to transfer efficiently from the cells to the coolant, while at the same time preventing any electrical contact between the metal pipe and the battery cells. At the bends of the cooling pipe, you'll notice a distinct orange-colored tape. This is Kapton tape, a special high-temperature insulating material used to enhance the electrical insulation in areas where the pipe changes direction or comes close to other components. The coolant flowing through these pipes is a mixture of water and glycol, the same type of solution used in many high-performance cooling systems. It's responsible for absorbing heat from the cells and carrying it away to maintain a stable temperature throughout the module. As the coolant moves through the battery pack, it gradually picks up heat from the cells, its temperature rising as it flows from one end of the module to the other. This temperature gradient, often shown in Tesla's thermal diagrams, perfectly illustrates how the cooling loop keeps every part of the battery operating safely and efficiently. An exploded view of the cell assembly inside the battery module clearly reveals that inside the battery module, the 18650 lithium-ion cells are held vertically, sandwiched between a pair of complementary cell inserts. The cell inserts are made of flame-retardant polycarbonate plastic and contain a multitude of complementary cylindrical retaining holes called cell wells. The cell wells in the cell inserts are through holes to keep the cell terminals exposed for making connections. On top of the cell inserts on each side of the module, current collector plates are placed. These current collector plates are made of copper and contain holes that align with the holes in the cell inserts, which ensures that the cell terminals remain exposed for making connections. Each cell terminal in the Tesla battery module is connected to the current collector plate using thin aluminum fuse wires. These fuse wires act as both electrical connections and safety devices. They allow current to flow from each cell into the module's power circuit, but if a cell ever overheats or short circuits, the fuse wire will instantly melt and disconnect that cell from the rest of the pack. These individual cell-level connections ensure that in the case of a short circuit event, the failure is isolated and the risk of sustained arcing and a thermal run is minimized. After the cells have been sandwiched between the top and bottom cell inserts, an adhesive such as Loctite is dispensed in the space between the cell ends and the cell insert. The adhesive is expected to penetrate the interstices and spaces between the cell and the cell insert. This adhesive securely bonds each cell to the cell insert. Alright, brain teaser time. Let's see how well you've been paying attention. Question 1. If one Tesla Model S battery module contains 444 cells, and the full battery pack uses 16 such modules, how many individual 18,650 cells are in the entire pack? We are sure you have been able to solve the question. Let's look at the solution. 444 modules in the battery pack is multiplied by 16 modules in the pack, which will give 7,104 cells in the battery pack. Question 2. If each 18,650 cell stores about 12.4 watt-hours, how much total energy, in kilowatt-hour, do all 7,104 cells store together? Again, quick mental math or use your phone. Answer time. Multiply 7,104 cells by 12.4 watts-hours per cell equals 88,089.6 watts-hours, which is about 88.09 kilowatt-hours of total stored energy. A quick note, you might sometimes see Tesla quoted as an 84 kilowatt-hour pack. That's because manufacturers often report usable capacity, what's available for driving, which can be slightly less than the total or nominal capacity we just calculated. So 88.09 kilowatt-hours is the rough total energy inside the cells. The usable figure can be lower after safety margins, battery management reserves, and rounding. Bonus question. What happens if one of the thin aluminum fuse wires connecting a cell to the collector plate melts? Think, does the whole pack fail? Drop the answer in the comment section. Thank you so much for watching today's video and learning how the Tesla Model S battery modules are put together. Remember, here at RoRe Academy YouTube Channel 2.0, you watch, learn, and understand how to prototype. See you in the next video. If you found this video insightful, don't forget to like, subscribe, turn on notifications, comment, and share, so you never miss our next deep dive into the world of technology and innovation.